Welcome back to GE Fun Facts Online. Today we are skipping the usual preamble because the topic we are discussing requires our full attention. We are diving deep into the intersection of quantum physics and artificial intelligence. Specifically, we are exploring a technology that might save AI from collapsing under its own weight: quantum model pruning. Let's start by setting the scene. Imagine the year is 2026. Artificial intelligence is no longer a novelty. It is the invisible infrastructure of the modern world. From writing software code to diagnosing complex diseases, large language models and deep neural networks are the engines driving civilization forward. But there's a massive problem. This engine is running dangerously hot. We are facing a paradox. As our AI models grow smarter, they are becoming unsustainably heavy. Back in 2020, GPT-3 shocked the world with 175 billion parameters. By 2024, models like GPT-4 and Llama 3 had pushed past the trillion parameter mark. Today, in our hypothetical 2026, the data centers required to run these frontier models consume as much electricity as entire nations. The carbon footprint of training just one of these digital brains exceeds the lifetime emissions of 5 cars. And that is just training. Inference, the act of actually using the model to answer your questions, drains gigawatts of power daily across the globe. We have hit what industry experts call the silicon wall. We cannot simply keep adding more GPUs and building bigger power plants. The physics of electricity and heat transfer won't allow it. We need a fundamental shift in how we construct these digital minds. We need to make them smaller, faster, and smarter, without losing the brilliance that makes them useful. This is where we leave the world of computer science and enter the world of high-energy physics. Enter quantum model pruning. It sounds like science fiction, but it is a solution rooted in the deepest laws of nature. It is the marriage of quantum mechanics and machine learning. This technique uses the mathematics of the subatomic world to slice away the fat of artificial intelligence, leaving only the pure muscle of intelligence behind. This isn't just about saving hard drive space. It is about green AI. It is about running ChatGPT-level intelligence locally on your smartphone. It is the story of how physics is saving AI from itself. To understand the solution, we have to truly understand the problem. Why are AI models so incredibly huge? Deep learning models are essentially massive grids of numbers called tensors. These tensors represent the weights or the strength of connections between artificial neurons. When you train a model, you are tuning these billions or trillions of weights to minimize errors. The problem arises from how we store these weights. They are stored in dense matrices. If you have a layer in a neural network with 10,000 input neurons and 10,000 output neurons, you need a matrix with 100 million numbers to describe the connections. As you add more layers and more neurons, the number of parameters explodes exponentially. This phenomenon is known as the curse of dimensionality. For years, engineers have tried to fight this curse with something called classical pruning. The concept is simple. They look at the weights, find the ones that are close to zero, meaning they don't contribute much to the output, and they delete them. They set them to zero. This works to a degree, but it is a blunt instrument. Imagine trying to make a race car lighter by randomly drilling holes in the chassis. Eventually, you compromise the structural integrity. Classical pruning ignores the relationships or correlations between the weights. It treats every number as an island. But in the quantum world, nothing is an island. Physicists have been dealing with this curse of dimensionality for nearly a century. In quantum mechanics, describing the state of a system with many interacting particles, like electrons in a superconductor, is a nightmare. The amount of information needed grows exponentially with every particle you add. A system with just a few hundred particles has more theoretically possible states than there are atoms in the observable universe. However, physicists noticed something remarkable. Nature does not use all those states. Most of that theoretical space is empty. Real physical systems, the ones that actually exist in our universe, occupy a tiny, highly structured corner of that massive possibility space. They are governed by entanglement and correlations. To describe these systems efficiently, physicists developed a mathematical toolkit called Tensor Networks. A tensor network is a method of compressing a massive, high-dimensional object into a chain of smaller, low-dimensional tensors connected together. Think of it like image compression. You realize that a complex image isn't just random noise. It is made of repeating patterns. If you store the rule for the pattern, rather than every single pixel, you save massive amounts of space. Around the late 2010s, a major epiphany occurred in the research community. Researchers realized that neural networks look exactly like quantum many-body systems. The layers of a neural network act like time steps in a quantum evolution. The weights of the network act like the interactions between particles. Most importantly, the intelligence of the model is hidden in the correlations between the weights, just like the properties of a material are hidden in the entanglement of its electrons. This meant we could take the tools designed to simulate quantum physics, tensor networks, and apply them to AI. we could tensorize the AI. So how does quantum model pruning actually work? Let's break down the mechanics without getting bogged down in jargon. At the heart of this technique is a concept called singular value decomposition, or SVD. Imagine a rectangular grid of numbers, a matrix. SVD breaks this grid into 3 smaller matrices. 2 of them describe the directions of the data, and the middle one describes the importance of each direction. If you have a matrix with 100 rows and 100 columns, but it only contains information that flows in 5 main directions, SVD will tell you that. You can then throw away the other 95 dimensions. You haven't just deleted random numbers, you have identified the underlying structure and discarded the noise. But deep learning models don't just use 2D matrices, they use multidimensional tensors. Standard SVD doesn't work well there. This is where tensor decomposition comes in. The most popular form for AI compression is the tensor train, also known as matrix product state decomposition. Imagine a giant Rubik's cube of numbers. That is your 3D tensor. A tensor train breaks this cube into a line of smaller cubes connected by bonds. The magic lies in something called the bond dimension. This number controls how much correlation or information is allowed to flow between the tensors. If the bond dimension is high, you keep all the information and get no compression. If the bond dimension is low, you compress the model heavily. In physics, this bond dimension is related to entanglement entropy. If a system has low entanglement, meaning the particles aren't talking to each other much, you can use a tiny bond dimension. It turns out neural networks have surprisingly low entanglement entropy. The weights are not random, they are highly correlated. This means we can crush a massive weight matrix into a thin tensor train with a small bond dimension, reducing the number of parameters by 90 to 99% while keeping the intelligence intact. Now you might ask, why is this better than the classical pruning we mentioned earlier? Classical pruning creates sparse matrices. These are essentially Swiss cheese, full of holes. Standard computer hardware, specifically GPUs, hates sparse matrices. GPUs are designed to crunch dense blocks of numbers. If you feed a GPU a Swiss cheese matrix, it spends half its time checking if a number is 0 rather than calculating. Quantum model pruning or tensorization creates smaller but dense matrices. Instead of a 1000 by 1000 matrix with holes, you get 2 1000 by 10 matrices. The GPU loves this. It can crunch these smaller dense matrices at lightning speed. The result is a model that is smaller, taking up less RAM, and significantly faster, offering lower latency. Classical pruning often saves RAM, but fails to speed things up without specialized hardware. Tensorization wins on both fronts. There are several ways researchers and startups like Multiverse Computing and Google X are applying these physics principles today. The first method is post-training tensorization, often called the compressor. This is the most common approach for handling existing giants like Llama 3 or GPT-4. You take a pre-trained model and identify the heaviest layers, usually the linear layers and attention heads. You apply tensor decomposition to these layers, effectively factorizing the large weight matrices into chains of smaller tensors. Because this decomposition is an approximation, the accuracy drops slightly. So you run a short training phase called fine-tuning or healing. The model learns to adjust its new, smaller brain to perform the same tasks. For example, a tool called Compactive AI by Multiverse Computing used this method to reduce the size of a Llama 2 model by 70% while retaining 98% of its accuracy. This allowed the model to run on a fraction of the memory and energy. Another method is quantum-inspired optimization, or the annealer. This approach uses algorithms inspired by quantum annealing. Imagine you are trying to find the absolute best configuration of weights to prune. This is an optimization problem with a rugged landscape of peaks and valleys. Classical algorithms can get stuck in a local minimum, a decent solution but not the best one. Quantum annealing relies on tunneling. Ideally, a quantum computer would look at the landscape and tunnel through the hills to find the true lowest valley, the optimal compressed model. Since we don't have powerful enough quantum computers yet, we use quantum-inspired evolutionary algorithms on classical hardware. These simulate the tunneling effect to find better pruning patterns than standard gradient descent ever could. The implications of quantum model pruning are transformative across 3 main pillars: energy, access, and privacy. Let's talk about the energy revolution. We mentioned that training Llama 3 consumes gigawatt hours. If we can compress these models by 50 to 80%, we slash the energy bill proportionally. Think about inference costs. For every token ChatGPT generates, it burns energy. If the model is 4 times smaller via tensorization, that is roughly 4 times less energy per token. Across billions of daily queries, this saves terawatt-hours of electricity annually. Next, consider AI on the edge. Currently, if you want to use a smart LLM, you need the cloud. Your phone sends a request to a massive server farm, which processes it and sends it back. This is slow, requires internet, and costs money. Quantum model pruning enables edge AI. By compressing a 70 billion parameter model down to a size that fits in 8 gigabytes or 12 gigabytes of RAM, you can run it locally on a high-end smartphone or a laptop. This means zero latency, instant responses, and reliability even when offline. Smart cameras, drones, and medical devices can have supercomputer intelligence without being tethered to a server. This leads directly to privacy and security. This is huge for industries like healthcare and finance. Hospitals cannot upload sensitive patient data to public servers due to privacy regulations. If they can take a powerful open-source model, compress it using quantum pruning, and run it on their own secure, local servers, or even on an iPad in the doctor's hand, the data never leaves the room. Quantum pruning bridges the gap between dumb but private local models and smart but public cloud models. Looking forward, we are currently in the quantum-inspired era. We are using classical computers to run algorithms borrowed from physics. But what happens when real quantum computers mature? We are looking at the holy grail, quantum data loading. One of the biggest bottlenecks in AI is loading data. Classical data is vast, but quantum states are efficient. Future quantum model pruning might involve QPU pruning, using a real quantum annealer to solve the optimization problem of which waits to cut millions of times faster than a GPU. Eventually, we won't just simulate tensor networks. We will run them natively on quantum processors. A tensor network is the native language of a quantum computer. While classical computers struggle to calculate tensor contractions sequentially, a quantum computer does it naturally. However, it is not all smooth sailing. Training a tensor network model from scratch is mathematically harder. The gradients, the signals used to learn, can vanish or explode more easily than in standard networks. Furthermore, there is an implementation barrier. Most AI engineers know PyTorch or TensorFlow. They don't know the physics of matrix product states. Tools like Google's Tensor Network library are bridging this gap, but the learning curve remains steep. In conclusion, quantum model pruning is more than just a compression algorithm. It is a convergence of two of the 20th century's greatest intellectual achievements, quantum mechanics and computer science. For decades, physicists struggled to simplify the complexity of the universe, developing tools to describe the entanglement of stars and atoms. Today, those same tools are taming the complexity of the artificial minds we have created. As we stare down the barrel of an energy crisis and a data wall, physics is the unexpected savior. It turns out that the best way to build a better brain is to understand how the universe organizes itself, not with brute force, but with elegant, correlated efficiency. The future of AI isn't just bigger, it's denser, smarter, and quantum compact. Thanks for listening to G Fun Facts Online.